Hey everyone, and welcome. Have you ever looked at your clothes and noticed how some of them shimmer and catch the light, while others just look, well, flat? It's not magic, it's physics. And today, we're going to pull back the curtain on the secret optics that are literally engineered into every single thread we wear. It's a question you've probably never thought to ask, but it's something we see every day. The answer is pretty amazing, and it all comes down to the journey a single beam of light takes when it hits a piece of fabric. So let's follow that beam of light, from the moment it hits the surface all the way down to the molecular level. So, first things first. Our story starts right at the surface of the fiber. This is the very first interaction, and it's what decides whether a fabric has that awesome, eye-catching shine or a more quiet, matte finish. Now, the official scientific term for this is luster. It sounds a little fancy, but all it really means is the total visual story of how light bounces off something. It's not just shiny or dull, it's the whole picture. And it's the first big piece of our puzzle. Okay, so light can bounce in two basic ways. On one hand, you've got specular reflection. Think of a mirror. Light hits it and bounces off in one clean, focused beam. Then you have diffuse reflection, where light hits a rougher surface and just scatters in every possible direction. A fabric's luster, it's always some kind of mix of these two. And what determines that mix? It's all about the texture of the fiber itself. A super smooth and regular fiber, like silk, acts like millions of tiny, perfect mirrors. That's what gives it that beautiful, high luster. But then you have something like cotton, which is rough and irregular. It scatters light all over the place, giving it that familiar, flat, low luster look. And this is where it gets really clever. This whole shine thing isn't just left up to nature. Nope. For man-made fibers, luster is an engineered quality. Scientists can actually dial it up or dial it down to get the exact look they're going for. So how do they do it? Well, check this out. On the left, you see a clear fiber reflecting light nice and cleanly. But on the right, they've added tiny particles of something like titanium dioxide. This stuff is called a delustrant, and it basically creates all these little internal surfaces that scatter the light before it can bounce back out. It's a super effective way to turn down the shine. All right, so we've covered what happens on the surface, but what about the light that doesn't bounce off, the light that actually goes inside the fiber? Well, this is where things get really, really interesting. To get what happens next, we have to talk about something called the refractive index. You've seen this in action a million times. You know how when you put a straw in a glass of water, it looks like it's bent or broken? That's because water and air have different refractive indices. It's just a way to measure how much a material slows down and bends light that passes through. But here's the twist. For simple stuff like water, the refractive index is the same no matter which way light travels through it. A textile fiber is different. It's not the same in all directions. It has a grain, a specific axis, and that changes everything. And that brings us to the absolute heart of textile optics. It's a property with a fantastic name, birefringence. I know it sounds super complicated, but the idea behind it is actually pretty easy to visualize. Let's break down the word. Birefringence. Bi for two, and refringence for, well, refraction. It literally means double refraction. It's what happens when a material has two different speed limits for light, depending on which way the light is oriented when it goes through. And this diagram shows it perfectly. A single beam of light goes into the fiber, and bam, it gets split in two. One part of the light travels parallel to the fiber's grain, and it experiences one refractive index. The other part travels perpendicular to the grain and experiences a completely different one. So, how do you measure this? It's surprisingly simple. The birefringent value is just the difference between those two refractive indices. You just subtract one from the other. But don't let that simple math fool you. That one number tells scientists a ton about what's going on inside that fiber. But why? Why does this split even happen in the first place? The answer isn't on the surface. It's deep inside, in the way the fiber is built molecule by molecule. It all comes down to molecular alignment. See, a fiber is made of these really long chain molecules, polymers, that are all stretched out and lined up along the fiber's main axis. It's a lot like the grain in a piece of wood. That physical alignment is what creates a difference in direction, and that's what causes the optical split. And we can get even more specific. The actual shape of those molecules fine-tunes the effect. If you have straight, neat chains like in picture A, you'll get a big difference in high birefringence. If the chains are more of a zigzag like in B, it reduces the effect. And if they have these bulky groups sticking off the sides like in C, it can reduce it so much that the value can even go negative. Just look at this comparison. Triacetate, which has those bulky side groups, has a tiny birefringence of 0.005. But terylene, which is a polyester with really straight aligned molecules, has a value of 0.188. That is almost 40 times higher. It's a perfect example of how much that hidden molecular structure controls what we see. Okay, so now we know that light travels differently inside a fiber depending on its direction. That lets us unlock one final secret: how this whole thing affects a fabric's color. And that brings us to our final concept called dichroism. Dichroism is what you get when you combine birefringence with dye. Since the fiber's own molecules are all lined up, the dye molecules tend to line up with them. And what that means is that the fiber will actually absorb the parallel and perpendicular parts of the light differently. This can totally change the richness and depth of the color you see. This image shows it so well. When the dyed fibers are all parallel, one part of the light gets absorbed, but the other part can kind of slip through. But when you cross the fibers, the first layer absorbs one part, and the second layer absorbs the other part. The end result is that way more light gets absorbed in total, making the color look much deeper and darker. So let's put it all together. The look of any fabric is basically a three-step story. Step 1, light hits the surface and reflects, creating luster. Step 2, the light that goes inside gets split by the fiber's aligned molecules. That's birefringence. And finally, step 3, that split light gets absorbed differently by oriented dye molecules, creating the final shade through dichroism. So the next time you're admiring the rich color of a shirt or the cool shimmer on a jacket, just remember what you're seeing isn't just a surface-level thing. It's a really complex dance between light and matter, something that's been engineered all the way down at the molecular level. It's pretty incredible. And all this leads to a really exciting final thought. We've pretty much mastered the optics of the fibers we have today. But as our ability to build materials gets more and more precise, literally atom by atom, what comes next? What kind of amazing, dynamic, beautiful new experiences are our future clothes going to provide? Thanks for joining us for this deep dive into the science of style.